Something has been throwing stars out of a galaxy for the last 400 million years. Not planets, not comets. Stars, heavier than our Sun, launched hard enough to escape not one galaxy but two, and they are arriving in the outskirts of the Milky Way right now. The class they belong to includes an object moving at roughly 50 times the speed of 3A Atlas, the fastest interstellar visitor humanity has ever measured. And when astronomers ran their trajectories backwards with the best data ever collected, roughly half of them converged on the same place. One spot inside the Large Magellanic Cloud, 160,000 light-years away. There should be a supermassive black hole sitting there. Nobody has ever detected it, in any wavelength, ever. Subscribe to the Sky Lab and hit that like button, because this story gets a sequel the moment somebody finds it. Drop a comment and tell me where you are watching from, and whether you have ever seen the Magellanic Clouds with your own eyes. Now, let's get into it. Part 1. The fastest thing we ever measured. On the 1st of July 2025, a telescope in Chile picked up a faint smudge of light that did not belong to us. It was moving wrong. Not fast in the way a comet is fast when the sun grabs it and slings it around, but fast in a way that meant it had never been ours to begin with. The survey that found it is called Atlas, and within days the orbit came back with a number attached that settled the argument permanently. The object was moving at roughly 57 kilometers per second relative to the Sun, measured out where the Sun's gravity barely matters. That is its cruising speed. That is how fast it was going before it ever met us, and it is how fast it will be going long after it has gone. We named it 3I Atlas, and for a year it was the fastest interstellar object humanity had ever measured. Millions of people watched it cross the sky. It became, for a while, the standard by which everyone measured speed in space, because it was the fastest thing anyone could point at and say, "That one, right there, that is not from here." I want you to hold on to 57 kilometers per second, because I am about to make it look like nothing. There is an object inside our own galaxy, catalogued as J0927-6335, and it is moving at approximately 2,800 kilometers per second. Run that division. It is 49 times faster than the fastest interstellar visitor we have ever recorded. Round it however you like. It is 50 times. That number is not a projection or a model output or somebody's enthusiastic estimate. Its heliocentric radial velocity, the component we can measure most directly, is 2,285 kilometers per second. Its total space velocity, once you account for the sideways motion as well, comes out at roughly 2,800. The characterization was done with ultraviolet spectroscopy and published in the journal Astronomy and Astrophysics in 2024 in volume 689, article L6. It is the fastest known star in our galaxy, and it took the record from a previous record holder, a white dwarf catalogued as D6-1, which had held the title for years. 2,800 kilometers per second is a hard number to feel, so let me put it somewhere useful. At that speed, you would cross the distance from the Earth to the Moon in about 2 minutes and 15 seconds. You would cross the entire diameter of the Earth in 4.5 seconds. If you left the Sun this morning at that speed, you would pass the orbit of Neptune before the end of next week. And here is what J0927 actually is, because the explanation matters for where this story goes. It is a white dwarf, the burnt-out core of a star that has already died once. It used to live in an extremely tight binary with another white dwarf, the two of them orbiting each other so closely and so quickly that their orbital speeds were themselves enormous. Then the other one detonated. A Type 1a supernova, one of the most violent events in the universe, and when it went off, the surviving partner was simply released. It had been whipping around at thousands of kilometers per second, held in place by a companion that stopped existing. So it left in a straight line at exactly the speed it had been travelling in its orbit, like a stone leaving a sling. The model has a name in the literature, and the name tells you how confident astronomers are about it. They call it the dynamically driven double degenerate double detonation scenario, which is a mouthful that gets shortened to D6. Two degenerate objects, meaning two white dwarfs. A double detonation, meaning the explosion propagates in 2 stages. And dynamically driven, meaning the whole thing is set off by the orbital dance itself rather than by some external event. J0927 is understood to be the surviving donor predicted by that model, which means its speed is not a mystery at all. Its speed is a measurement of how fast it was already going. That is a complete explanation. It is elegant, it fits, and it involves nothing we do not understand, which is why J0927, for all its speed, is not the mystery. The mystery is the ones that arrive in groups. There is a whole class of these objects, and astronomers call them hypervelocity stars. The definition sounds technical and is actually quite blunt. A hypervelocity star is one moving fast enough to escape the gravity of the entire galaxy it lives in, not fast enough to leave its neighbourhood, not fast enough to get thrown into a wide orbit and come back in a few 100 million years, fast enough to leave, permanently, and never return. To understand how extreme that is, you need a sense of what the Milky Way's grip actually feels like. Out here, where we are, the escape velocity of our galaxy is somewhere around 550 kilometers per second. That is the speed you would need to break free from the combined gravitational pull of a few 100 billion stars and a great deal of dark matter. Our own Sun, for reference, is orbiting the centre of the galaxy at about 220 kilometers per second. It is moving quickly by any human standard, and it is comfortably, permanently bound. It is going nowhere. An unbound star is one that has cleared 550 and kept going. There is a survey that has spent years looking for exactly these objects, and as of the most recent analysis it had accumulated 21 of them. 21 unbound, late B-type main sequence stars, sitting out in the sparse outer halo of the Milky Way, every one of them moving fast enough to leave and never come back. For decades, the assumption about where they came from was straightforward. There is one object in our galaxy with enough gravitational violence to do this, and it sits at the centre. Sagittarius A star, our own supermassive black hole, roughly 4 million times the mass of the Sun. Everyone assumed the stars were coming from there. It made sense. It was the only thing that made sense. Then somebody ran the trajectories backwards with the best measurements ever taken, and roughly half of them did not go there. They went somewhere else. They went out of the galaxy entirely, across 160,000 light-years of empty space, and converged on a small, bright, disorderly companion galaxy that hangs in the southern sky and can be seen with the naked eye from anywhere below the equator. The Large Magellanic Cloud. It is worth understanding what that object is, because most people in the Northern Hemisphere have never seen it. It is the largest and brightest satellite galaxy the Milky Way has, containing roughly 1/10 of our galaxy's stellar mass. It has a prominent bar running through its middle, and an irregular, unsettled shape that comes from being pulled at continuously, by us and by its smaller companion. To the naked eye it looks like a detached piece of the Milky Way that somebody left behind. Southern Hemisphere sailors used it for navigation for centuries before it had a European name, and it eventually took the one it carries now from Ferdinand Magellan's expedition, which described it on the voyage around the world in the 1520s. 160,000 light-years is a distance that resists intuition, so anchor it this way. Light leaving that galaxy right now will not arrive here until roughly the year 162,000. The light you can see from it tonight left when our species had not yet walked out of Africa, and a star thrown out of it does not travel at the speed of light. It travels at a few 100 kilometers per second, which means the ones arriving in our halo now have been in transit for tens of millions of years at minimum, which creates a problem, because the mechanism that makes hypervelocity stars requires a supermassive black hole. That is not a preference. It is a requirement of the physics. If half of these stars were launched from the Large Magellanic Cloud, then the Large Magellanic Cloud has to contain a supermassive black hole of roughly 600,000 solar masses. Nobody has ever seen it. There is no bright accretion disk at the centre of that galaxy. There is no X-ray point source. There is no radio core of the kind that made Sagittarius A star famous decades before anyone managed to photograph its shadow. Nobody has measured a sphere of influence by watching stars whip around an invisible mass. Every survey we have pointed at the Large Magellanic Cloud, in every wavelength we know how to collect, has come back with nothing. We have an object we can weigh but cannot find. We know approximately how heavy it is. We can even estimate where it sits, to within about 1.5 degrees of sky. And in the entire history of astronomy, nobody has ever recorded a single photon that we can confidently say came from it. The only evidence that it exists at all is the wreckage, stars that left, and the direction their paths point when you run the film backwards. So what exactly are we looking at? Something is standing in the middle of a galaxy 160,000 light-years away, picking up stars and throwing them hard enough to escape not one galaxy but two. It has been doing it for at least 400 million years, and it has never once shown itself. Part 2. What 57 kilometers per second actually means. Before we take 3I Atlas apart as a measuring stick, it deserves a moment of respect because it earned the record honestly, and the numbers behind it are genuinely strange. The most extreme thing about that object was never its speed. It was the shape of its path. Every orbit in the solar system has a number attached called eccentricity, which describes how stretched it is. A perfect circle has an eccentricity of 0. The Earth's orbit is nearly circular at about 0.017. A long-period comet on a wild elliptical loop might reach 0.99, spending centuries out in the dark and a few frantic months near the Sun. Anything at exactly 1 is right on the boundary, on a parabolic path marginally unbound. Anything above 1 is hyperbolic, which means it is not in orbit at all. It is passing through. 3I Atlas came in with an eccentricity of 6.145. That is not a slightly unbound orbit. That is by a wide margin the most extreme hyperbolic trajectory ever recorded inside our solar system, and it is what an object looks like when the Sun's gravity is essentially a rounding error against the speed it already has. The Sun bent its path, gave it a temporary shove, and then it kept going in almost exactly the direction it had been going before it arrived. It reached its closest approach to the Sun on the 29th of October 2025 at about 1.36 astronomical units. That is inside the orbit of Mars and outside the orbit of Earth, which is worth saying clearly because a great deal of nonsense circulated at the time about how close it came to us. It did not come close to us. At perihelion, with the Sun's gravity temporarily adding to its speed, it peaked at roughly 68 kilometers per second, which was widely reported as around 130,000 miles per hour. And when it left, and the Sun's contribution fell away, it settled back to the number that actually describes it. 57 kilometers per second. That is the figure astronomers call the hyperbolic excess velocity, and it is the honest one, because it strips out everything the Sun temporarily lent it, and leaves you with the object's own speed through interstellar space. For scale against the only two comparable objects we have ever seen, the first interstellar visitor, discovered in 2017, was travelling at roughly 26 kilometers per second. The second, discovered in 2019, at roughly 32. 3I Atlas was moving at nearly twice the speed of either one, which is why it took the record and why it is the right benchmark for this video. It is the fastest thing from outside that we have ever confirmed and measured. There is a detail buried in that comparison that most coverage skipped, and it is relevant to where we are going. An object's interstellar speed is a fingerprint of its age. Stars in the galaxy do not all move together. The young ones, born recently from gas that is still settling into the disk, move in fairly orderly circles at fairly similar speeds. The old ones have been jostled for billions of years by every passing star, every spiral arm, every molecular cloud they drifted through, and their orbits have been steadily randomized. So the older a population is, the wider the spread of its velocities. An object moving at 57 kilometers per second relative to us is not a young object. It has been bounced around for a very long time. That is the reasoning that produced the widely repeated claim that 3I Atlas might be extremely old, and it is a kinematic inference rather than a direct measurement, which is exactly the kind of distinction this channel exists to make clearly. Now, let me build you a ladder, because the numbers only start to mean something when you can see them stacked. Escape velocity is the whole game here, and it works the same way at every scale. To leave the surface of the Earth entirely, ignoring the atmosphere, you need 11.2 kilometers per second. To leave the solar system from where the Earth sits, you need about 42 kilometers per second relative to the Sun. To leave the Milky Way from where we are, you need somewhere around 550. Notice what happens across those three numbers. Going from the Earth's surface to the edge of the solar system costs you roughly a factor of 4 in speed. Going from the edge of the solar system to the edge of the galaxy costs you another factor of 13. Gravity does not scale gently. Every time you widen the scope of what you're trying to escape, the price goes up faster than the size of the thing, because you are not fighting one object anymore. You are fighting the summed pull of everything inside your orbit, and out here that means several 100 billion stars plus a halo of dark matter that outweighs all of them combined. So here is the ladder, rung by rung. 3. The Atlas sits at 57 kilometers per second, fast enough to cross between star systems, and nowhere near fast enough to leave a galaxy. It is bound to the Milky Way. It always was. It will spend the rest of its existence looping through the galaxy just like every other thing in here. That point gets missed constantly, so let me be precise about it. 3I Atlas is interstellar, not intergalactic. It escaped a star system. It did not escape a galaxy, and it never will. It arrived here from somewhere else in the Milky Way. It is leaving towards somewhere else in the Milky Way, and in a few 100 million years it will still be circling the same galactic centre we are circling, just on a wilder orbit than ours. Everything above it on this ladder is in a different category entirely. Those objects are leaving for good. The next rung up is the population this video is actually about. The stars ejected from the Large Magellanic Cloud, left at somewhere between 400 and 600 kilometers per second. Call it 7 to 10 times 3, or Atlas. Above that sits a specific star called HE 0437-5439, moving at 723 kilometers per second, roughly 13 times. Above that, the stars we believe were thrown by our own galaxy's central black hole, with typical ejection velocities around 870 kilometers per second. Roughly 15 times, then a jump. A star catalogued as S5HVS1, moving at 1,755 kilometers per second, 31 times 3I Atlas, and at the top, J0927, at approximately 2,800, 49 times. I want to be straight with you about something, because I would rather you trust me than be impressed by me. That 50 times figure at the top of the ladder belongs to the record holder. It is a single object with a single, well-understood, and rather violent origin story. The group, the population that this whole video is built around, sits much lower down. 7 to 10 times 3 I Atlas at ejection. That is the honest number for the Magellanic stars, and I would argue the group is by far the stranger half of the story, for a reason that has nothing to do with speed. A record only requires one unusual event. Somewhere in the galaxy, at some point, one binary system got unlucky in exactly the right way, and one white dwarf walked away from it at 2,800 kilometers per second. That is remarkable, and it is also a coincidence in the most literal sense. It happened once. A group requires a factory. When you find 9 or 10 objects that all share a speed range, all share a stellar type, all arrive from roughly the same patch of sky, and all trace back to the same point in space, you are no longer looking at an accident. You are looking at the output of something that does this repeatedly. Something with a mechanism, a rate, and an address. Every rung on that ladder above about 400 kilometers per second has the same requirement sitting underneath it. To throw an entire star that hard, you need something extraordinarily massive and extraordinarily compact, and the list of things in the universe that qualify is very short. The question this video keeps circling back to is not whether such a thing exists in the Large Magellanic Cloud. The physics is fairly insistent that it must. The question is why, after all this time, we still cannot see it. Part 3. The Slingshot. In 1988, an astronomer named Jack Hills published a paper describing a way to throw a star out of a galaxy. At the time, this was pure theory. Nobody had found a hypervelocity star. Nobody had confirmed a supermassive black hole at the centre of the Milky Way. Hills was describing a mechanism that, as far as anyone knew, might never have happened anywhere. It took another 16 years before the first candidate turned up, and by then the paper had been sitting there, quietly correct, waiting for the observations to catch up. The gap between the prediction and the confirmation is worth pausing on, because it says something about how this field operates. Hills wrote down the mechanism in 1988. The first strong hypervelocity star candidate was not identified until 2005. That is a 17-year wait for a theory to acquire an example, and during those 17 years the paper was not fashionable, not disputed, and not particularly discussed. It was simply correct and unemployed. Astronomy is full of results like that, sitting in journals, waiting for a telescope that has not been built yet. The mechanism is worth walking through slowly, because everything that follows depends on it, and because it is genuinely one of the more elegant pieces of gravitational physics you will encounter. Start with a binary star system. 2 stars, orbiting a common centre of mass bound to each other. This is not exotic. A very large fraction of the stars in any galaxy live in binaries, and among massive young stars the fraction is higher still. Where you have hot, heavy stars, you tend to have pairs. Now let that binary's orbit around the galaxy carry it inward, toward the centre, and let it pass close to a supermassive black hole. As the pair approaches, something specific starts to happen. The black hole's gravity is not uniform across the space the binary occupies. The star that happens to be nearer the black hole at any moment feels a stronger pull than the star further away. That difference in pull across the separation between the 2 stars is what we call a tidal field. It is the same phenomenon that raises the oceans on Earth, operating with vastly more violence. Right up until a certain distance, the binary holds together. The 2 stars are gravitationally attached to each other, and that attachment is stronger than the difference in pull trying to separate them. Then they cross a threshold, and the balance flips. Inside a boundary called the tidal radius, the black hole's tidal field exceeds the binary's own self-gravity. The stars stop being a pair. In terms of energy, they are now 2 independent objects moving through an extremely steep gravitational well, and the well is about to sort them. What happens next is a transaction, and it obeys the same bookkeeping that governs every gravitational slingshot ever performed. Total energy is conserved, so one star loses and the other gains. The loser falls inward. It gives up orbital energy and drops into a tight, fast orbit around the black hole, where it will remain, circling something that will eventually consume it. The winner takes everything the destroyed binary had. All the orbital energy that used to hold the 2 stars together gets dumped into a single object, and that object leaves at a speed it could never have achieved on its own. In the extreme cases, that departure speed exceeds 1,000 kilometers per second. The star that leaves is a hypervelocity star. The star that stays is evidence in principle, though it is far too close to the black hole for us to pick out individually at these distances. In our own galaxy, we can actually see the leftovers. There is a population of stars orbiting Sagittarius, a star at extraordinarily close range, tracked for decades by teams who watch them complete entire orbits around something invisible. Those observations are what proved our central black hole exists in the first place, and they won a Nobel Prize for it. A fraction of that inner population is thought to consist of exactly these captured partners, the losing halves of binaries that were pulled apart. So the mechanism leaves 2 kinds of fingerprint. It leaves stars sprinting away from the galaxy forever, and it leaves stars trapped in tight loops around the object that broke them up. We have found both, in the one place close enough to look properly. Now, the reason this matters for what we are trying to work out is that the calculation runs in both directions. The inputs to a Hill's ejection are specific and countable. You need the mass of the black hole. You need the masses of the 2 stars in the binary. You need how far apart they were before the disruption, and you need the pericenter distance, meaning how close the pair came to the black hole at their nearest approach. Feed those 4 numbers in, and the physics gives you 2 things back: the probability that an ejection happens at all, and the speed the escaping star leaves at. Which means if you can observe the escaping stars, count them, and measure how fast they're going, you can run the whole thing backwards and solve for the mass of the object that threw them. That is exactly what has been done here. That is where the 600,000 solar masses comes from. Not from seeing anything, from measuring the debris and inverting the equation. But before we get to that, I want to give you the case that removes any doubt about whether this actually happens, because it is one of the cleanest results in modern astronomy, and it is not from the Large Magellanic Cloud at all. It is from right here. In 2020, Sergei Koposov and colleagues published a paper in the monthly notices of the Royal Astronomical Society, volume 491, page 2465. The preprint version carried a title that tells you what they thought they had found. They called it the Great Escape. The object is a star catalogued as S5HVS1. It is an A-type main sequence star sitting roughly 9 kiloparsecs from the Sun, which is to say around 30,000 light-years away. and it is moving at 1,755 kilometers per second. That number was, at the time, nearly twice the velocity of any hypervelocity star previously associated with our galactic centre. It was not a marginal case. It was not a star that might be unbound depending on which mass model you preferred. It was leaving, and it was leaving faster than anything anyone had linked to Sagittarius a star before. Then they ran the trajectory backwards. The path did not point vaguely toward the inner galaxy. It did not converge on a broad region and leave room for argument. Integrated backwards through the Milky Way's gravitational field, the orbit of S5 GVS1 points unambiguously at the galactic centre. The inferred ejection velocity, at the moment it left Sagittarius A star, was approximately 1,800 kilometers per second. And the travel time since that moment is about 4.8 million years. 4.8 million years ago, that star was in a binary orbiting close to the black hole at the centre of our galaxy. Something reached in, took its companion and threw it out. It has been travelling ever since, and it has crossed 30,000 light years, and it is still going, and it will keep going after it clears the galaxy entirely. There is your proof of concept, not a simulation, not a statistical inference across a population. One star, one unambiguous backtrack, one supermassive black hole with a well-measured mass, and a departure speed that matches what the mechanism predicts. So the question in the Large Magellanic Cloud is not whether supermassive black holes can throw stars this hard. That argument is over. We have watched it happen in our own galaxy, and we can name the star it happened to. The question is, what is doing it over there? Because if the mechanism is real, and it is, and if roughly half of the unbound stars in our outer halo trace back to a galaxy where no black hole has ever been detected, then one of two things is true. Either the mechanism does not apply, and something else entirely is accelerating these stars, or there is an object of 600,000 solar masses sitting 160,000 light-years away that is hidden from every instrument we have ever built. Neither of those is a comfortable sentence, and only one of them can be right. Part 4. 21 stars that are never coming back. Forget the record holder. From here on, this video is about the group. There is a research program that has spent years doing nothing but hunting for these objects. It is called, with admirable directness, the HVS Survey, and its entire purpose is to find stars in the Milky Way that are moving fast enough to leave it. That sounds like it should be easy. It is not. And understanding why is the first step to understanding why the result matters. The problem is that speed alone is not enough. To prove a star is unbound, you need 3 separate measurements, and all of them have to be good. You need its distance, because escape velocity changes depending on where in the galaxy you're standing. You need its radial velocity, meaning how fast it is moving toward you, or away from you, which you get from the Doppler shift in its spectrum. And you need its proper motion, meaning how fast it is drifting sideways across the sky, which is the hardest of the 3 by an enormous margin. Get any one of them wrong and a bound star can masquerade as an escaping one, or the reverse. The survey's answer to that problem was to be extremely picky about what it looked at. The sample is 21 unbound, late B-type, main sequence stars, sitting out in the sparse outer halo of the Milky Way. Every part of that description is doing work. B-type stars are hot and blue and bright. That last quality is the practical one, because these objects are enormously far away, and anything dimmer would simply not be detectable at the distances involved. A late B-type star, meaning one at the cooler end of that class, is bright enough to be picked out tens of thousands of light-years from here, and has a spectrum with clean, well-understood absorption lines. Those lines are what give you a reliable distance and a reliable radial velocity. Choose a star with a messy spectrum and your error bars swallow the answer. Main sequence matters because it pins down the star's actual brightness. A main sequence star of a given colour has a known luminosity, so if you measure how bright it appears you can calculate how far away it must be. A giant or supergiant of the same colour could be vastly brighter and vastly further, and you would have no way to tell the difference without more information. But the property that makes B-type stars genuinely diagnostic, rather than merely convenient, is that they do not last long. A massive, hot star burns through its hydrogen at a ferocious rate. Where our Sun will run for roughly 10 billion years, a B-type star of a few solar masses might get a few 100 million. That is a strict physical stopwatch, and it puts a hard ceiling on how far one of these objects could possibly have travelled. If you find a young B-type star 50,000 light-years from any place capable of forming stars, and its speed says it would have taken longer than its own lifetime to get there, then something is wrong with your assumption about where it started. That constraint is going to do a great deal of work later in this video, and I want you to have it in hand before we need it. The outer halo, meanwhile, is essentially empty. Picture the Milky Way's familiar spiral as a thin, bright disk, roughly 100,000 light-years across and only a few thousand light-years thick. Now picture a vast, sparse, roughly spherical cloud surrounding all of it, extending far above and below the disk, populated by scattered ancient stars and globular clusters and very little else. There is almost no gas out there, and effectively no star formation. A hot, young, massive B-type star has no business existing in the outer halo at all, because nothing out there could have made it. So every star in this sample is already an anomaly before you measure its speed. Each one is a young object in a place where young objects are not manufactured, which means each one is a traveller. That logic is worth making explicit, because it is the reason this survey looked where it did. If you want to find stars that have been thrown a long way, do not search the disk, where the galaxy is busy manufacturing new stars all the time and a young blue object proves nothing. Search the empty regions, where the presence of a young blue object is itself the anomaly, and where the only available explanation is that it came from somewhere else. The outer halo is not a difficult place to search. It is a place where the signal has almost no background to hide in. The other thing that lives out in the halo is globular clusters, and they are worth a sentence because they establish the contrast. A globular cluster is a tightly packed ball of a few 100,000 ancient stars, gravitationally bound, orbiting the Milky Way as a unit. Some of them are 12 or 13 billion years old. They are essentially the oldest structures in the galaxy, and everything in them is red, cool, and long past its prime. That is what the outer halo is supposed to contain. A hot blue B-type star out there, moving at hundreds of kilometers per second, is as out of place as it is possible for an object to be. And then you measure the speed, and you find they are all above the line. Unbound means what it sounds like. These 21 stars are not on wide, slow orbits that will eventually bring them back around in 500 million years. They have exceeded the escape velocity of the entire Milky Way. They are leaving. Every one of them is on a one-way trip out into intergalactic space, and no gravitational structure they are ever likely to encounter will be sufficient to turn them around. Sit with the scale of that for a moment. The nearest large galaxy to us is Andromeda, and it is 2.5 million light-years away. The space between galaxies is not like the space between stars. It is emptier by an almost unimaginable factor. A star crossing it is crossing a region where you could travel for 1 million years in any direction and pass nothing at all. These stars are on that road. They will still be on it when the sun has swollen into a red giant, thrown off its atmosphere entirely and shrunk into a cinder. Now, the paper that reorganized everything about how we understand this sample was published in 2025. The lead author is Jiwon Jesse Han, with Sangmo Tony Sohn, Karim El Badri, Lars Hernquist, and Charlie Conroy. It appeared in the Astrophysical Journal, volume 982, article 188, and it was posted to the Archive preprint server on the 31st of January, 2025. The title of the paper is not a question. It reads, "Hypervelocity stars trace a supermassive black hole in the Large Magellanic Cloud." That is a claim, and the authors clearly meant it as one. Buried in the results is a number that changes the character of the whole thing. When they worked out when each of the Magellanic origin stars was launched, the ejection times spread across a range from roughly 30 million years ago to roughly 400 million years ago. Think about what that spread rules out. If all 21 stars had been ejected at once, you could imagine a single catastrophic event, some one-time collision or merger, that flung a handful of stars out and then was over. A single event would leave a single date. This is not a single date. This is a process that was running 400 million years ago, was still running 30 million years ago, and has no obvious reason to have stopped. Whatever sits at the centre of the Large Magellanic Cloud has been catching binary stars and tearing them apart for at least 370 million years of continuous operation. That is not an accident. That is a machine with a duty cycle. You can even reason about the rate, roughly, and the arithmetic is sobering. 9 confidently identified stars spread across 370 million years works out to something on the order of 1 detected ejection every 40 million years. But that is only what we can see, and what we can see is filtered several times over. It only counts the stars bright enough and hot enough to be found at these distances. It only counts the ones launched in a favourable direction, for reasons we will get to shortly. And it only counts the ones that happen to be crossing our observable region right now, rather than having already passed through and gone. The true rate has to be considerably higher than 1 every 40 million years. We are seeing the tip of something. There is one more implication of that time span that I want to plant before we move on. 400 million years ago, life on Earth had only just begun colonizing land. The stars ejected at the far end of that range left before there were forests. They have been in flight through the space between 2 galaxies for the entire span of complex life on this planet, and they are only now passing through the outer edge of our own. And nobody has ever photographed the thing that launched them. Part 5. Running the film backwards. Here is the thing that makes all of this possible, and it is not a telescope pointed at a black hole. It is arithmetic. If you know where a star is, how far away it is, how fast it is moving toward or away from you, and how fast it is drifting across the sky, then you know its full 3-dimensional velocity through the galaxy. And if you also know the shape of the gravitational field it has been moving through, you can take that velocity and run it backwards in time. You can rewind the star. The star does not have to cooperate. It does not have to still be near where it started. It does not have to leave a trail. Gravity is deterministic, and a well-measured orbit is a recording that plays in both directions. For most of the history of astronomy, one of those 4 numbers was missing. Distance we could estimate. Radial velocity we have been able to measure since the 1860s, because the Doppler shift in a star's spectrum tells you directly whether it is approaching or receding, and by how much. But proper motion, the sideways drift, was the killer. A star at 50,000 light-years moving at 500 kilometers per second across your line of sight shifts its apparent position by an almost imperceptible amount over a human lifetime. We are talking about fractions of 1,000th of an arcsecond per year. That is roughly equivalent to watching a coin from 1,000 kilometers away and trying to notice it slide sideways. Without that number, a backtrack is not a calculation. It is a guess with error bars wide enough to include most of the sky. Then Gaia happened. The European Space Agency's Gaia mission spent years doing one thing with obsessive precision, measuring the positions and motions of well over 1 billion stars. Its third data release delivered proper motions of a quality that had simply never existed before. And what that unlocked was not new objects. The hypervelocity stars were already catalogued. What it unlocked was the ability to ask with real confidence where each of them came from. The way Gaia achieved that is worth understanding, because it explains why nothing before it could. The spacecraft did not stare at individual stars. It spun slowly and continuously, sweeping 2 separate fields of view across the entire sky over and over again, measuring the angular separation between stars in one field and stars in the other. Every star got observed dozens of times from slightly different positions as the spacecraft moved along its own orbit. Out of that pile of repeated measurements, you can extract 3 things simultaneously: the star's position, its distance through parallax, and the steady drift of its position year over year. It is a survey built specifically to solve the sideways motion problem, and it solved it for over 1 billion objects at once. Nothing in ground-based astronomy comes close, and the reason is the atmosphere. Looking up through several kilometers of turbulent air smears every point of light into a shimmering blob. You can average that out, and people did for decades, but there is a floor below which you cannot go from the ground. Getting above the atmosphere removes the floor entirely, so that is what Han and colleagues did. They took all 21 stars, attached Gaia's proper motions to the existing distances and radial velocities, and adopted a model of the combined gravitational field of the Milky Way and the Large Magellanic Cloud together. That second part matters more than it sounds. The Large Magellanic Cloud is massive enough to visibly distort our galaxy's gravitational field, and if you rewind a star through a Milky Way that pretends its largest satellite does not exist, you get the wrong answer. The reason the Large Magellanic Cloud has to be in the model at all comes down to mass. Estimates of its total mass, including its dark matter halo, run high enough that it is not a minor perturbation on our galaxy. It is massive enough to pull the Milky Way's own centre of mass around, massive enough to warp our outer disk, and massive enough to bend the path of anything travelling through the outer halo. If you rewind a star through a gravitational field that leaves out an object of that size, the backtrack will drift off course by an amount that grows with every million years you rewind. Over hundreds of millions of years, that error is not a rounding difference. It is the whole answer. And here is the awkward part stated plainly. The Large Magellanic Cloud's total mass is still debated. Different estimates disagree substantially, and which one you believe depends partly on whether you think the galaxy is on its first pass around us, or has been in orbit for far longer. So the model that the backtracks depend on has a genuine open question sitting inside it. That does not invalidate the result. It does mean the result carries an assumption, and Honest Work says so. Then they propagated the uncertainties, which is the part that separates careful work from a press release. Every input has an error bar. The distance has an error bar. The radial velocity has an error bar. The proper motion, even from Gaia, has an error bar. So the output is not a single line traced backwards through space. It is a cone of possibility that widens the further back you go, and the honest question is not where does this star come from, but rather what fraction of that cone lands on each candidate origin. And when they ran it, the cones did not all point where everyone expected. Roughly half of the 21 did not converge on the centre of our galaxy. Approximately 9 of them are confidently classified as having come from the Large Magellanic Cloud. Roughly 7 prefer an origin at the galactic centre. The remainder sit in between, ambiguous, with cones broad enough to accommodate either. I want to be careful with language here, because this is exactly where popular coverage tends to overreach. Traces back to does not mean somebody watched the path. It means that when you integrate the orbit backwards with all the measurement uncertainties included, the probability distribution favours that origin. It is a statement about likelihood, not a photograph of a journey. That is not a weakness of the result. It is how essentially all of galactic dynamics works. But it is worth saying out loud, because the difference between a strong inference and an observation is the difference this whole video turns on. Now, why was that result surprising? Because for decades there was only one suspect. Sagittarius A star sits at the centre of the Milky Way with roughly 4 million solar masses, and it is the most thoroughly studied supermassive black hole in existence. We have tracked individual stars through complete orbits around it. We have measured its mass to a precision that would have seemed absurd a generation ago. When hypervelocity stars started turning up in the 2000s, the immediate and entirely reasonable assumption was that Sagittarius A star had made all of them. There was nothing else in range that could. The Gaia result breaks that assumption in a specific and uncomfortable way. It says that a smaller object, in a smaller galaxy, 160,000 light-years away, an object that has never been detected in any wavelength by any instrument, appears to be outproducing our own galaxy's central engine in this particular sample. There are good reasons for that which we will get to, and they are not mysterious. But the raw shape of the finding is genuinely strange. The best studied black hole in the universe is being outthrown by one nobody can find. The film runs backwards cleanly. It travels out of our galaxy, crosses the gap, and arrives at a galaxy we can see perfectly well with our own eyes. And then it stops at a specific spot inside it, and at that spot there is nothing. Part 6. Why they all arrive from Leo. If the stars were being thrown at random, they would arrive from everywhere. That is the expectation you should have. A black hole sitting at the centre of a galaxy, catching binary systems that wander in from all directions, has no preferred axis. Binaries approach it on every possible trajectory. The ejections should spray outward in a roughly spherical pattern, and from our vantage point 160,000 light-years away, the resulting hypervelocity stars should be scattered across the sky with no particular pattern. That is not what we see. The Magellanic origin hypervelocity stars cluster. They arrive preferentially from one region of sky in the direction of the constellation Leo. When a result like that turns up, there are only 2 possibilities. Either it is a fluke of small numbers, or something is imposing a direction on the process. And in this case, the explanation is not only known, it was worked out and published before the observations confirmed it. Here is the mechanism, and it is almost embarrassingly simple once you see it. The Large Magellanic Cloud is not sitting still. It is a galaxy in orbit around the Milky Way, and it is moving through space at a considerable speed. Every star inside it is being carried along with it. the same way everything in your car is travelling at the car's speed whether it knows it or not. Now throw a star out of a moving galaxy. The star does not just get the speed the black hole gave it, it gets that speed added to the motion it already had, which is the galaxy's own orbital motion. And the addition depends entirely on direction. If the black hole happens to throw the star roughly forward in the same direction the galaxy is already travelling, the two velocities add together. The star gets an extra boost of approximately 300 kilometers per second on top of whatever it was given. If the black hole throws the star roughly backward against the galaxy's motion, those same 300 kilometers per second are subtracted instead. 300 kilometers per second is not a small correction. Remember that the ejection velocities we are talking about are in the range of 400 to 600 kilometers per second. So a forward-launched star might arrive at 700 or 900. A backward-launched star from the identical ejection might come out at 100 to 300, which is nowhere near enough to escape. Two identical events, two stars given exactly the same kick by exactly the same object. One of them ends up in our outer halo as a catalogued hypervelocity star, and the other one never gets anywhere at all. The only difference between them is which way the black hole happened to be pointing at the moment the binary came apart, and the black hole was not pointing on purpose. It was just geometry. That is a much stranger idea than it sounds, and it is worth holding for a moment. The population we have found is not a sample of what the Large Magellanic Cloud produces. It is a sample of what survives a filter we did not design and cannot switch off, and there is your one-sided sky. The forward-launched stars are preferentially pushed over the threshold into fast, unbound, detectable hypervelocity. The backward-launched ones mostly are not. They stay in the Large Magellanic Cloud, or they drift out slowly and get captured by the Milky Way, or they simply never reach the speeds that would make anyone notice them. So the population we can actually see is not the population that was ejected. It is a filtered version of it, and the filter has a direction. That direction, projected onto our sky from where we happen to be sitting, points at Leo. What makes this genuinely compelling, rather than merely a tidy story told after the fact, is the timing. In 2016, Douglas Boubert and colleagues published a paper with the title A Dipole on the Sky. Predictions for hypervelocity stars from the Large Magellanic Cloud. They laid out the asymmetry as a prediction. They said, if this mechanism is operating in the Large Magellanic Cloud, then the hypervelocity stars will not be evenly distributed. They will show a lopsided pattern with a preferred direction, and here is roughly where that direction should point. Then Gaia's proper motions arrived, and the pattern was there. A prediction that lands before the data is worth vastly more than an explanation constructed afterwards. Anybody can look at a pattern and invent a reason for it. Very few reasons survive being written down in advance and then tested against measurements that did not exist when they were proposed. The word dipole in that title is doing precise work, and it is not decoration. A dipole means a two-sided pattern, an excess in one direction and a matching deficit in the opposite direction. That is a very specific signature, and it is not the same as a random clump. A random clump could happen by chance with small numbers, and with only 9 or 10 confidently identified stars you should absolutely worry about that. But a dipole is structured. It says there is an axis, and the axis has a preferred end, and the preferred end is the direction the parent galaxy is travelling. That structure is what makes the pattern hard to dismiss as a statistical accident, because chance produces clumps far more readily than it produces oriented dipoles that happen to line up with an independently measured orbital velocity. And this is the point at which the alternative explanations start running into serious trouble. There are other ways to make a fast star, and they are real. Supernova kicks work. If one star in a binary explodes, the surviving partner is released at its orbital speed, which is the same physics that produced our record holder. Dynamical ejections work too. In a dense young star cluster, 3 and 4 body gravitational encounters can slingshot a star out at high speed, and Gaia has found dozens of runaway stars in the Large Magellanic Cloud that were almost certainly produced this way. But both of those mechanisms have the same fatal property for this particular problem. They eject in effectively random directions. A supernova does not know which way the galaxy is moving. A chaotic encounter between 3 stars in a cluster has no preferred axis. Neither one produces a dipole on the sky. And on top of that, both mechanisms struggle badly to reach these speeds for massive stars. Classical dynamical ejection models for stars of this mass have real difficulty getting much above a few hundred kilometers per second. Pushing past that requires either extraordinarily tight encounters, which are correspondingly rare, or something far more compact and massive than an ordinary star. So any competing explanation has to clear 3 bars at once. It has to produce the speeds, it has to produce the angular clustering, and it has to produce them at a rate consistent with how many of these stars we actually find. Individually, alternatives can manage one. Nobody has managed all 3 simultaneously. There is a further wrinkle that makes the alternatives even harder to sustain. Whatever mechanism you propose has to run inside the Large Magellanic Cloud specifically, and that galaxy has a low escape velocity compared with ours. A star only needs a modest push to get out of it. So if random dynamical ejections in star clusters were producing this population, the Large Magellanic Cloud should be leaking stars in every direction at a healthy rate, and most of them should be arriving in our halo from a broad spread of angles rather than a narrow cone. The clustering is not just unexplained by the alternatives, it is actively predicted against by them. One clarification before we move on, because it trips people up. The stars are not from Leo. Leo is a pattern of foreground stars in our own galaxy that happens to lie along that line of sight. What we are describing is a direction, not a destination. These objects are simply passing through that region of our sky on their way out of the galaxy, and in a few million years they will appear somewhere else entirely. An entire population of escaping stars arrives from one patch of sky, because one galaxy is moving in one direction and something at the centre of it is throwing. Part 7. The Star That Changed Sides. 3 times. I want to slow down and look at a single object, because its history tells you more about how this science actually works than any summary of results could. The star is catalogued as HE 0437-5439. It also carries the designation HVS3, which marks it as the 3rd hypervelocity star ever identified. It is moving at 723 kilometers per second. That is roughly 2,600,000 kilometers per hour, or about 1,600,000 miles per hour. It is a massive unbound main-sequence B-type star, and it is comfortably above the Milky Way's escape velocity, and its position is where the trouble starts, because it sits only about 65,000 light-years from the Large Magellanic Cloud. That is close. Suspiciously close. Close enough that when it was first characterized, the obvious question was immediate. Why would a star ejected from the center of our galaxy happen to be sitting right next door to a completely different galaxy? The argument that followed has now run for nearly 2 decades, and it has changed direction 3 times. Round 1 arrives in 2005 and 2006, when the star is identified as an unbound hypervelocity main-sequence B star. And almost immediately a problem appears. Remember the stopwatch built into these objects. This is a massive, hot, short-lived star. Work out how long it would take to travel from the galactic center to where it currently sits, at 723 kilometers per second, and the answer is uncomfortably close to, or longer than, the star's entire possible lifetime. The star would have had to be born, ejected, and cross an enormous distance, and still be shining as a main-sequence B star at the end of it. The numbers do not sit comfortably together. If it came from the Large Magellanic Cloud, the problem evaporates. It is a much shorter trip. Round 2 arrives in 2008, and it comes from chemistry rather than motion. Somebody took a high-resolution spectrum of the star and measured the abundances of individual elements in its atmosphere with real precision. Metallicity came back at roughly half solar, and the pattern of abundances, the relative proportions of the various elements, did not match the pattern seen in stars near the galactic center. It matched the pattern seen in the Large Magellanic Cloud. This is powerful evidence, and it is worth explaining why. A star's atmosphere preserves the chemical composition of the gas cloud it condensed out of. Different galaxies enrich their gas at different rates and through different histories, so they develop different chemical signatures, like regional accents. The Large Magellanic Cloud is less chemically evolved than the inner Milky Way, and it shows. A star carries that accent with it forever, no matter how far it travels or how fast. The reason those signatures differ comes down to how many generations of stars a galaxy has already burned through. Everything heavier than helium was manufactured inside stars and released when they died. So a galaxy that has been forming and destroying stars vigorously for billions of years accumulates heavy elements faster than a smaller, quieter one. The inner Milky Way is chemically rich because it has been running that cycle hard for a very long time. The Large Magellanic Cloud, smaller and less efficient at it, has not. Half solar metallicity is exactly what you would expect from a star born over there, and precisely not what you would expect from one born near our galactic centre, where the gas is enriched well above solar. And this evidence has a property the kinematic evidence does not have. Chemistry does not depend on any assumption about gravitational fields, or galaxy masses, or orbital histories. You take a spectrum, you measure line strengths, you get abundances. There is no model in between the measurement and the conclusion. One of the papers that year carried a title that made its position explicit. It was called LMC Origin of the Hypervelocity Star HE 0437-5439, Beyond the Supermassive Black Hole Paradigm, so by 2008 the case looked closed. The travel time argued for the Large Magellanic Cloud. The chemistry argued for the Large Magellanic Cloud. Two independent lines of evidence pointing the same way. Round 3 arrives in 2010, and it overturns both of them. Astronomers used the Hubble Space Telescope to measure the star's proper motion directly, which at that point was the most precise measurement of its sideways drift anyone had achieved. They published under the title A Galactic Origin for HE 0437-5439, the hypervelocity star near the Large Magellanic Cloud. And the measurement ruled out an origin at the centre of the Large Magellanic Cloud at the 3 sigma level. Statistically, it said the star did not come from there. 3 sigma is worth unpacking because the phrase gets used loosely and it means something specific. It describes how far a measurement sits from a hypothesis in units of its own uncertainty. 3 sigma corresponds to roughly a 1 in 300 chance that the result arose from measurement error alone if the hypothesis were true. That is strong. It is not, however, the 5 sigma threshold that particle physicists demand before announcing a discovery, and results at 3 sigma have a long history in every field of occasionally reversing when better instruments arrive, which is exactly what happened here. That is how things stood for 15 years. The kinematics said Milky Way, the chemistry said Large Magellanic Cloud, and the field mostly deferred to the kinematics, because motion is more direct evidence about origin than composition is. The chemistry camp, meanwhile, had an answer for the kinematic result, and it was not a dismissal. Their point was that a proper motion measurement of a faint star 50,000 light-years away, made over a baseline of a few years, is one of the hardest measurements in observational astronomy. A tiny systematic error in the reference frame used to define what stationary means will translate into a large error in the inferred origin once you rewind hundreds of millions of years. That was not an accusation. It was a statement about how error compounds over long integrations, and it turned out to be the correct concern. Round 4 is the 2025 paper we have been discussing, with Gaia's proper motions, which are better than what Hubble could deliver for this object, and with an updated model of the combined Milky Way and Large Magellanic Cloud gravitational field. Han and colleagues put HE 0437-5439 back in the Magellanic camp. It is one of 3 stars, along with HVS7 and HVS15, that they identify as having the highest likelihood of a Magellanic origin, on the grounds that their orbits are incompatible with an ejection from the galactic centre. Now step back and notice what actually happened across those 4 rounds. The kinematic argument reversed itself twice. Better data changed the answer, then better data changed it back. That is not a failure. That is measurement uncertainty behaving exactly as it should, with each generation of instruments narrowing the error bars and occasionally moving the central value. But the chemistry never moved. From 2008 onward, the abundance pattern said the same thing it says today. It said this star was born in the Large Magellanic Cloud, and it kept saying it through 15 years during which the kinematic consensus disagreed. There is something worth taking from that, and it is not a lesson about who was right. It is that 2 completely independent methods, measuring completely different physical properties, argued with each other for 18 years until the instruments got good enough to settle it. Nobody suppressed anything. Nobody was embarrassed. The disagreement was published openly in journals anyone can read, and it was resolved the only way disagreements in this field ever get resolved, which is by waiting for a better telescope. And when it was resolved, the answer was the uncomfortable one. Something in the Large Magellanic Cloud threw a star heavier than our Sun hard enough to escape not one galaxy, but two, and it has been doing that for hundreds of millions of years, and we still have absolutely no idea what it looks like. Part 8. 600,000 suns. We have spent this entire video describing the stars. Now we describe the thing that threw them, and we are going to do it without ever looking at it, because nobody has managed that yet. What follows is the process by which you can weigh an object you cannot see, using nothing but the debris it has produced, and it is one of the more remarkable pieces of reasoning in modern astrophysics. Go back to the Hills mechanism for a moment. Remember that it takes 4 inputs: the mass of the black hole, the masses of the 2 stars in the binary, how far apart those stars were before disruption, and how close the pair came to the black hole. Feed those in, and you get 2 outputs: the probability that an ejection occurs and the speed of the star that escapes. The important word in that sentence is mass. The ejection velocity depends on how massive the black hole is. A more massive black hole has a deeper gravitational well, which means the tidal disruption happens further out, which means more energy is available for the transaction, which means the escaping star leaves faster. So the relationship runs both ways. If you can measure the speeds of the escaping stars and you know roughly what kind of binaries were being fed into the machine, you can solve for the mass of the machine. That alone would give you a rough answer with wide error bars. Han and colleagues did something more careful than that. They used a second constraint, and it is the cleverer half of the argument. They compared the number of Magellanic hypervelocity stars to the number of galactic center ones in the same sample. Think about why that helps. Sagittarius A star has a mass we know extremely well, because we have watched stars orbit it for decades. It is roughly 4 million solar masses, so we know from the physics how many hypervelocity stars an object of that mass should be producing, and how fast they should be going. That gives us a calibrated reference. Now count how many stars in the same survey, found by the same methods, with the same detection thresholds, came from the Large Magellanic Cloud instead. If the Magellanic object were producing them at a similar rate, it would have to be of a similar mass. If it were producing far fewer, it would be smaller. If more, larger. You're effectively running a controlled experiment where the Milky Way's black hole is the control group. The answer that comes out of that analysis is approximately 6 times 10 to the 5th solar masses, roughly 600,000 times the mass of the Sun. Set that against Sagittarius A star's 4 million, and you get a ratio of about 7 to 1. The object in the Large Magellanic Cloud is roughly 7 times lighter than ours. And now we hit the inversion I flagged earlier, which is the genuinely odd part of this result. The smaller object appears to be outproducing the larger one. In this sample, roughly 9 stars trace to the Magellanic black hole and roughly 7 to Sagittarius A star. The lighter, unseen, undetected object is winning. There are 2 entirely legitimate reasons for that, and I want to give them properly rather than leaving the paradox hanging for effect. The first is escape velocity, and it works in the Magellanic object's favour enormously. To become a hypervelocity star escaping the Milky Way, a star ejected from our own galactic centre has to fight its way out from the deepest point of the deepest gravitational well in the neighbourhood. It gets thrown at, say, 870 kilometers per second, and then it spends the next 100 million years climbing, losing speed the whole way, and it only counts as unbound if it still has enough left when it reaches the outer halo. An enormous fraction of the stars Sagittarius A star throws simply do not make it out. They arc up, slow down, and fall back. A star ejected from the Large Magellanic Cloud has a much easier time. That galaxy has roughly 1/10 of our stellar mass, and its own gravitational well is correspondingly shallow. A star only needs a modest push to leave it entirely, and once it is out, it is not starting from the bottom of the Milky Way's well. It is starting 160,000 light-years away, near the top of it. The second reason is the boost we already covered. The Large Magellanic Cloud's orbital motion adds 300 kilometers per second to forward-launched stars, which promotes a whole tranche of ejections over the detection threshold that would otherwise have fallen short. Sagittarius A star sits near the centre of our galaxy and has no comparable running start. Both effects are in the analysis. Both are accounted for. And after you account for both, there is still a real result underneath, which is that something with roughly 600,000 solar masses is sitting in that galaxy doing this regularly. Now 600,000 solar masses is a strange number, and it is worth explaining why astronomers find it awkward rather than comfortable. Black holes, as far as we can currently census them, come in two well-populated categories. There are stellar mass black holes, formed when massive stars collapse, running from a few solar masses up to a few tens, and there are supermassive black holes, sitting at the centers of large galaxies, running from a few million solar masses up to tens of billions. Between those two populations, there is a gap in our catalogue, spanning roughly 100 to 100,000 solar masses, sometimes called the intermediate mass range. We have candidates. We have some strong ones. We do not have anything like the confident, well-measured population we have at either end. 600,000 solar masses sits just above that gap, at the very bottom edge of the supermassive category. It is exactly the kind of object our surveys are worst at finding, in exactly the mass range where our understanding of how these things form is weakest. It is also an awkward size for the galaxy it lives in. There is a well-known relationship between the mass of a galaxy and the mass of the black hole at its centre, and it holds across an enormous range. Bigger galaxy, bigger black hole. That relationship is one of the more unsettling results in extragalactic astronomy, and it is worth a moment. A galaxy is enormous. A black hole at its centre, even a supermassive one, occupies a region so small by comparison that the vast majority of the galaxy's stars have no idea it exists. The gravitational influence of a central black hole falls away long before you reach the bulk of the stars, and yet the two masses track each other tightly across galaxies of wildly different sizes, shapes and histories. Something ties them together, and the leading explanations involve feedback. As the black hole feeds, it blazes, and the radiation and outflows it produces blow gas out of the surrounding region, shutting down both its own food supply and the galaxy's star formation at the same time. The black hole and the galaxy regulate each other. Bigger galaxy, bigger black hole. The usual explanation involves mergers. Galaxies collide, their central black holes eventually sink together and combine, and the whole system grows in step. The Large Magellanic Cloud is a dwarf galaxy, with no obvious history of the kind of major mergers that would grow a black hole to this size, which does not make it impossible. The honest position is that our census of this mass range is so poor that unexpected is not the same as unlikely. We may simply be discovering that dwarf galaxies routinely host these objects, and we have never had a method sensitive enough to notice. Let me finish this part by giving you a physical sense of the object we are discussing, because 600,000 solar masses is an abstraction until you put a size on it. The event horizon of a black hole scales directly with its mass. For 600,000 solar masses, the radius of that horizon comes out at roughly 1.8 million kilometers. The diameter is therefore something like 3.6 million kilometers, which is about 2.5 times the diameter of the Sun. So the thing we're talking about is, in terms of the region it occupies, not enormous. You could fit it comfortably inside the orbit of Mercury with room left over. It is a sphere a couple of times wider than our star, containing more mass than every star in a large globular cluster combined, and it is completely, perfectly dark. We have a mass, we have an implied size, we have an approximate address, and we have never seen it. Part 9. Why we have never seen it. Let me lay out the non-detections one at a time, because the completeness of the failure is the point. There is no accretion disk at the centre of the Large Magellanic Cloud. There is no X-ray point source where the backtracks converge. There is no compact radio core. Nobody has measured a sphere of influence by watching stars accelerate around an unseen mass. Every wavelength we know how to collect, from radio through infrared through optical through X-ray, has been pointed at that galaxy repeatedly, and none of them has produced an object. To understand why that is both frustrating and completely unsurprising, you need to be clear about something that gets muddled constantly in popular coverage. We have never seen a black hole, not one, not ever. Black holes do not emit light. That is the entire definition. What we detect in every single case is the material around them. When gas and dust and torn apart stars spiral inward, they form a disk, and that disk gets compressed and sheared and heated to temperatures where it radiates ferociously across the spectrum. The famous images of black hole shadows are images of glowing material with a dark region in the middle where the light cannot escape. We photograph the absence by photographing what surrounds it, which means a black hole with nothing to eat is a black hole you cannot find, and that is not an exotic condition. Across most of cosmic history, Most supermassive black holes are quiet. The bright, blazing, active galactic nuclei that dominate popular imagination are a minority, and usually a temporary phase. The default state of a supermassive black hole is starvation, and a starving black hole produces essentially nothing. The physics of why is straightforward and slightly counterintuitive. A black hole cannot simply inhale everything nearby. Material falling toward it carries angular momentum, which means it does not fall straight in. It spirals, forms a disk, and has to shed that angular momentum through friction and turbulence before any of it can actually cross the horizon. That process is slow, and it depends entirely on how much gas happens to be within reach in the first place. Put a supermassive black hole in a region that has already been swept clear of gas, and it will sit there, dark and enormous, doing nothing measurable for hundreds of millions of years at a stretch, which is why the phrase we should be using is not that the black hole is hiding. It is not hiding. It is simply not doing anything, and the universe has no obligation to make idle objects visible. Our own galaxy is the proof of that. Sagittarius A star is remarkably faint for its mass. It is a famously underfed object, accreting at a tiny fraction of what it theoretically could, and its quiescence is one of the standing puzzles in the field. Proving it existed took decades of patient work tracking individual stars through complete orbits around a point of empty sky, and that work only became possible because it is 26,000 light-years away, which by the standards of this discussion is essentially in our lap. Now scale that difficulty up. The object in the Large Magellanic Cloud is roughly 7 times less massive. It is about 6 times further away, and it sits inside a galaxy that is actively forming stars, which means it is full of gas and dust that scatter and absorb optical light, which means the view is worse before you even start. Every factor runs the wrong way at once. Smaller target, greater distance, dirtier line of sight. The dust problem in particular deserves more than a mention, because it is not a minor inconvenience. Interstellar dust does not block light evenly. It scatters and absorbs short wavelengths far more efficiently than long ones, which is why distant regions of the galaxy look reddened, and why some regions of active star formation are essentially opaque in visible light. The Large Magellanic Cloud is forming stars vigorously, which means it is generously supplied with exactly the material that ruins an optical search. You can get around this by observing in the infrared, which penetrates dust far better, and people do. But infrared observing brings its own difficulties, including a sky that glows in the same wavelengths you are trying to measure, and it does not make a quiet object suddenly start radiating. There is one more factor, and it may be the most important one, because it is actionable. The Large Magellanic Cloud's dynamical center, meaning the point everything actually orbits, may not coincide with its optical center, meaning the brightest region where you would naturally point a telescope. Galaxies as disturbed as this one, being pulled at by 2 other galaxies simultaneously, do not necessarily keep their mass centered on their light. And when the hypervelocity star trajectories are used to locate the ejection site directly, that site comes out roughly 1.5 degrees away from the optical center. 1.5 degrees does not sound like much. On the sky, it is about 3 full moon widths. That is an enormous distance when you are conducting a deep, narrow field search with a large telescope, because those instruments see a tiny patch at a time, and every pointing costs observing time that somebody had to compete for. So it is entirely possible that the reason nobody has found this object is that everybody has been searching the bright, obvious middle of the galaxy, and the object is not there. That is a testable claim, and it comes with coordinates. There is a strange echo here to something we covered yesterday, in the video about the dead rocket stage falling toward the moon. That story turned on the same tension. We can calculate the moment of a collision on another world down to a fraction of a second, and we may not be able to see the flash when it happens. Precision of prediction, poverty of observation. We are extremely good at working out where something must be. We are much worse at looking at it. Now, if the black hole is not simply hiding, there are alternatives, and they deserve a fair hearing. The first is that the black hole is not at the center at all, because it never settled there or was knocked out of position. Galaxies merge constantly over cosmic time, and when they do, their central black holes are delivered into the combined system, and then have to spiral inward, which can take an extremely long time. A black hole that has not finished sinking, or that was displaced by a merger, sits off-centre in a region with far less gas available. That would explain the offset and the silence with a single mechanism, which is the kind of economy that usually indicates you are on the right track. The second alternative removes the central black hole entirely. Instead of one object of 600,000 solar masses, imagine several intermediate mass black holes, each a few hundred to a few thousand solar masses, sitting inside the dense young star clusters that the Large Magellanic Cloud has in abundance. Each one could disrupt binaries locally and eject stars by the same Hill's mechanism, just at lower individual speeds and from scattered locations. That is a real possibility, and it makes a specific prediction that distinguishes it. Multiple scattered sources would not produce backtracks converging on a single point. They would produce a diffuse spread of origins across the face of the galaxy. So the tightness of the convergence is the test, and as the sample grows, that test gets sharper. The third alternative is the one nobody likes to say out loud. It is not there. There is no black hole. The Hill's mechanism is not what made these stars, and something we have not thought of is responsible. The trouble with that option is that the 21 stars still exist and still have to have come from somewhere, and every natural alternative anyone has proposed fails to produce the speeds and the clustering and the rate all at once. Absence of evidence here is a statement about telescopes, but it is only a statement about telescopes until somebody points one at the right coordinate and it still comes back empty. Part 10. The Needle's Eye. Everything up to this point has used the same logical direction. Assume you know the Large Magellanic Cloud's orbit, rewind the stars and find out where they were launched. One paper published in 2025 turns that around completely. It is titled Threading the Magellanic Needle. Hypervelocity Stars Trace, the Past Location of the LMC, and it appeared in the Astrophysical Journal, volume 993, article L10. The reasoning goes like this. Take the three stars with the strongest case for a Magellanic origin, HVS3, which is the object we spent an entire part discussing, along with HVS7 and HVS15. Integrate their orbits backwards until each one arrives at its launch point. Now, here is the move. Those launch points are not all at the same time. The three stars were ejected at different moments spread across that 30 to 400 million year window. So each backtrack tells you where the Large Magellanic Cloud was at a particular past moment, not where it is now. String those positions together and you have a series of constraints on the galaxy's actual path through space. The true orbit of the Large Magellanic Cloud has to pass through every one of those points at the right time. The paper's own metaphor for that constraint is the one in its title, a needle's eye that the orbit must thread. And when you apply that constraint to the existing catalogue of proposed orbits for the Large Magellanic Cloud, most of them fail. Two survive. One is a first passage trajectory, drawn from a self-consistent hydrodynamic simulation. That model says the Large Magellanic Cloud is a newcomer, falling toward the Milky Way for the first time, only recently captured, and that everything we see of the interaction between the two galaxies is the opening act. The other is a second passage trajectory, from a collisionless N-body simulation. That model says the Large Magellanic Cloud has been here before. It came in, swung around, went back out, and is now on its second approach. Those are very different histories, and the difference matters for reasons well beyond this story. If the Large Magellanic Cloud is on its first pass, then its dark matter halo is essentially intact. Its mass is at the high end of the estimates, and it has not yet had material stripped away by repeated encounters. If it is on its second pass, then it has already been through the shredder once, it has lost mass, and the debris from that first encounter is out there somewhere. This argument has a history worth knowing, because it was a genuine upheaval when it started. For most of the 20th century, the assumption was comfortable and unexamined. The Magellanic Clouds were long-standing satellites, bound to the Milky Way, orbiting us for billions of years, and the Magellanic Stream was gas-stripped out of them during previous passes. Then somebody measured the Large Magellanic Cloud's sideways motion properly, and the number came back higher than expected. High enough that the galaxy might not be bound to us in any long-term sense at all. High enough that it looked less like a satellite in a settled orbit, and more like an object falling in for the very first time. That measurement reopened a question everybody had considered closed, and it has not been fully closed since. The first passage idea explains the high velocity naturally, and it explains why the Large Magellanic Cloud still holds so much gas, since a galaxy that had already been through the Milky Way's halo repeatedly should have had that gas stripped away long ago. But it also creates a problem, because it makes the Magellanic Stream harder to explain. If they have never been here before, what pulled that gas out? Which is precisely why an independent constraint on the past orbit is worth so much. And that is what a handful of escaping stars just delivered. That question feeds directly back into everything else in this video, because remember what the backtracks depend on. They depend on a model of the combined gravitational field, and that model depends on the Large Magellanic Cloud's mass, and its mass depends on which orbital history you believe. The reasoning is genuinely circular, and the way you break a circle like that is by finding independent constraints, which is exactly what these stars provide. That is the claim the paper makes for its own significance, and it is a fair one. Hypervelocity stars are the first dynamical tracer capable of constraining where the Large Magellanic Cloud used to be. Every other method tells you about its present state. These stars are messengers carrying a timestamp, and the timestamp is the launch date. It is worth pausing on the elegance of that. A handful of stars ejected by an object nobody has ever seen are now being used to reconstruct the orbital history of an entire galaxy over hundreds of millions of years. The debris turned out to carry more information than anyone expected, and it is worth taking a moment on the galaxy itself, because we have been treating it as a location rather than an object. The Large Magellanic Cloud sits roughly 160,000 light-years away, and holds something like 1/10 of the Milky Way's stellar mass. It is not a small thing. If it were sitting on its own in empty space, we would call it a respectable galaxy. It only looks minor because it is next to us. Its structure is disorderly in a way that is itself informative. It has a prominent bar running across it, offset oddly from what should be its centre. It has no clean spiral pattern, its shape is irregular, and star formation is proceeding vigorously across it, which is what a galaxy looks like when it is being gravitationally stirred. It is being stirred by two things. It is interacting with the small Magellanic Cloud, its own smaller companion, and the two of them are interacting with us. That three-body relationship has already had visible consequences. There is a vast trail of hydrogen gas stretched across the southern sky, pulled out of the Magellanic system by tidal forces and strung out behind it. It is called the Magellanic Stream, and it is 100 degrees long on the sky, which is to say it wraps across a substantial fraction of the entire celestial sphere. So the galaxy at the centre of this story is not a quiet, stable object, with a black hole sitting neatly in its middle. It is a galaxy being torn at from two directions, with its mass distribution unsettled, its centre possibly displaced, and gas being pulled out of it in a stream longer than most constellations. The same debris that reveals the black hole reveals the galaxy's history. A handful of escaping stars turn out to carry the record of where their home has been for the last 400 million years, which is a remarkable amount of information to extract from objects that are, from our point of view, simply leaving. Part 11. What would count as proof? At some point, somebody has to ask the uncomfortable question, so let me ask it plainly. What would it actually take for this to stop being an inference and start being a detection? There are three routes, and they are not equally promising. The first is the direct one. Point something powerful at the coordinate the backtracks converge on, roughly 1.5 degrees from the bright optical centre, and look for anything at all. A faint X-ray point source, a compact radio object, an infrared excess. Something that says there is an object here rather than merely an interesting patch of galaxy. The advantage of this route is that it is cheap in principle. You need observing time, not new hardware. The disadvantage is that if the black hole is genuinely starving, there may be nothing to see at any wavelength, and a non-detection will not settle anything. It never does. Failing to find something faint only tells you it is fainter than your instrument, which is a limit rather than an answer. The second route is the one that actually worked for our own galaxy. Measure the motions of stars near the suspected position, and look for the signature of a central mass. Stars orbiting a concentrated object move faster the closer they get, in a very specific pattern, and that pattern is unmistakable once you can resolve it. That is how Sagittarius A star went from hypothesis to established fact. The problem is angular size. The region where a black hole's gravity dominates over the surrounding stars is called its sphere of influence, and for 600,000 solar masses at 160,000 light-years, that region subtends an extremely small angle on the sky. You would need to resolve individual stars inside it, measure their motions precisely, and do it for enough of them to establish a pattern. That is at or beyond the edge of what current instruments can deliver, though not obviously beyond what the next generation of extremely large telescopes might manage. And that generation is arriving. There are ground-based telescopes under construction now, with primary mirrors measured in tens of meters rather than the 8 to 10 meters, that represent the current state of the art, and they are being built with adaptive optic systems designed from the outset to cancel out atmospheric blurring in real time. Angular resolution scales directly with mirror diameter. Tripling the aperture triples your ability to separate two stars that appear close together, which is exactly the capability this measurement requires. The Sagittarius A star result took roughly 3 decades of patient observation with the best instruments of the era. There is no obvious reason the same approach fails at the Large Magellanic Cloud, other than that it will be harder and take longer, and nobody has started. The third route is simply more stars. The entire result rests on 21 objects, of which roughly 9 carry the Magellanic classification confidently. That is a small number, and everybody involved knows it. 9 objects is enough to make a strong argument and nowhere near enough to close one. There is a comparison here to something we covered earlier this month, in the video about the 85-mile-wide comet drifting in from the outer solar system. The point of that story was that the largest object of its kind was almost certainly not exceptional, just the first one big enough and close enough to notice, and that the population it belongs to is mostly invisible to us. The situation here has the same shape. 21 hypervelocity stars are not 21 hypervelocity stars. They are the ones bright enough, hot enough, close enough, and favourably enough aimed to have been catalogued. The real population is larger, and we are reasoning about it from a sample we did not get to design. So, what happens when the sample grows? If the Magellanic fraction holds up in a sample several times larger, the case moves from strong inference to something very close to established. It becomes difficult to argue that 9 objects out of 21 are a statistical fluke, when it is 90 out of 210 and the dipole is still pointing the same direction. If it does not hold up, everything reopens at once. There are 2 ways that sample could grow, and both are already in motion. The first is more spectroscopy. Finding a hypervelocity star candidate is comparatively easy. Confirming one requires a spectrum good enough to nail down its type, its distance and its radial velocity, and telescope time for that is the bottleneck. Large multi-object spectroscopic surveys, which can capture hundreds or thousands of spectra in a single pointing, are the obvious tool. The second is more astrometry. Gaia has continued observing well beyond the data release these results are built on, and every additional year of observations lengthens the baseline over which proper motions are measured. A longer baseline means smaller errors, and smaller errors mean tighter backtracks. Some of the stars currently classified as ambiguous will stop being ambiguous. Some may switch sides, exactly as our friend from Part 7 did 3 times already. And there are real dependencies in this result that a larger sample would also stress test. The backtracks depend on the assumed mass distribution of the Milky Way. They depend on the assumed orbit of the Large Magellanic Cloud, which as we just discussed has 2 surviving possibilities that imply different masses. The survey targeted late B-type stars specifically, which means the sample says nothing about what other kinds of stars are being ejected. And the orbital boost preferentially promotes forward-launched stars into detectability, which means we are looking at a filtered population by construction. None of those are hidden. All of them are stated in the papers. But they are the kind of thing that gets lost between a journal and a headline, and they matter, because they are the reason this remains an inference. Here is what I find genuinely impressive about the whole structure, and I want to say it clearly because it is easy to mistake honest uncertainty for weakness. This is a good scientific claim precisely because it can be killed. It does not merely explain what we already see, it makes predictions. It says a black hole of a specific mass sits at a specific location. It says the sky distribution should have a specific orientation. It says a larger sample should preserve a specific ratio. Every one of those can be checked, and any one of them coming back wrong would do serious damage to the whole picture. Compare that to an explanation that can absorb any observation without changing. Such explanations feel satisfying and cost nothing because nothing can ever contradict them. We have named an object. We have weighed it. We have given it an address to within about 1.5 degrees of sky. We have worked out roughly how often it eats, and roughly how long it has been doing so, and we have never received a single photon from it. Part 12. If it isn't gravity. There is another explanation for all of this, and I am going to give it a fair hearing, because dismissing an idea without examining it is not skepticism. It is laziness wearing skepticism's coat. The argument runs like this. We have a population of stars moving at speeds that ordinary stellar physics struggles to produce. We have a required source object of 600,000 solar masses that nobody has ever detected in any wavelength despite decades of looking. And we have alternative natural mechanisms that consistently fail to reproduce the full pattern. So what if the acceleration is not gravitational at all? What if something is deliberately moving these stars? Before you dismiss that, understand where it comes from, because it did not originate in a comment section. The idea of deliberately moving a star has a real literature behind it. It appears in serious speculative engineering papers and in the techno-signature literature, which is the branch of astronomy concerned with what an advanced civilization's activities might look like from a distance. It is a recognized category, it has a taxonomy, and people with credentials have worked out the physics of it in some detail. The concept is called a stellar engine, and the designs come in classes. Class A is the simplest, and it's named after the physicist who proposed it. In 1987, Leonidas Shkadov described what is now called a Shkadov thruster, and the elegance of it is that it involves no exotic physics whatsoever. Here is how it works. A star radiates light in every direction, and light carries momentum. Ordinarily, that momentum pushes outward symmetrically, so the net force on the star is zero. Now build an enormous curved mirror and park it on one side of the star, held in position by balancing its own gravitational attraction against the radiation pressure pushing it away. That mirror reflects a portion of the starlight that would have escaped in one direction back the other way. Suddenly the radiation is no longer symmetric. There is more momentum leaving one side than the other, and the star, obeying the same conservation law that governs every rocket ever built, begins to accelerate in the opposite direction. The thrust available is roughly the star's total luminosity divided by the speed of light. That is a small number in absolute terms, and it produces an acceleration you would need extremely sensitive instruments to detect over a human lifetime. But it never stops. It requires no fuel, no maintenance in the conventional sense, and no ongoing energy input, because the star supplies everything. Run it for a few million years and you have meaningfully altered the trajectory of an object weighing more than 1 million times the Earth. Now here is the part that gives this idea traction in this specific context, and I want to be honest about it rather than skip past it. The thrust scales with luminosity. A star like our Sun is a poor candidate because it simply does not put out enough light to push itself around efficiently. But hot, massive blue stars are enormously more luminous. An O or B type star can be tens of thousands of times brighter than the Sun, which makes it a vastly better engine. And the hypervelocity population we have spent this entire video discussing is dominated by exactly those spectral types. Late B-type main sequence stars, the precise category that a Shkadov thruster would work best on. That is a coincidence, and I am pointing it out rather than hiding it, because if I only presented the facts that support the conclusion I have already reached, you would be right not to trust me. The correlation is real. We will come back to what it does and does not imply. There is a question sitting underneath all of this that is worth asking before we go further, which is why anyone would bother. Moving a star is an absurd undertaking. What could possibly justify it? The literature offers several answers, and they are more reasonable than you might expect. A civilization might want to escape a dangerous region of its galaxy, such as an approaching supernova or the increasingly hostile environment near a galactic center. It might want to rearrange the stars in its neighborhood to bring resources closer together, or to reduce the travel times between systems it has already settled. It might want to steer its home star away from a close encounter with another star that would disrupt its planetary system. Over long enough timescales, all of those are real problems with real deadlines, and a civilization thinking on a scale of tens of millions of years might treat them the way we treat flood defenses. Class B is the next rung up in ambition. Instead of a passive mirror that merely reflects, you build a partial Dyson swarm, a shell of collectors surrounding some fraction of the star. That structure does not just bounce light back, it absorbs the energy, processes it, and re-emits it as a directed beam or a stream of accelerated plasma pointed precisely where you want the thrust to go. The swarm idea itself is older than the thruster. Freeman Dyson described the general concept in 1960, and although his name got attached to the popular image of a solid shell enclosing a star, that was never what he actually proposed. He was clear that a rigid sphere would be structurally impossible. What he described was a swarm of independent objects, each in its own orbit, collectively intercepting a large fraction of a star's output. He also made the point that this channel keeps returning to in a different context, that such a structure would be detectable by its waste heat, radiating in the infrared. That observation is what turned a thought experiment into an actual observational search program, and people have been running versions of it ever since. The advantages over Class A are efficiency and control. A mirror gives you one direction, fixed by where you parked it. A powered swarm gives you steering, throttle, and considerably more thrust per unit of intercepted starlight. Class C and beyond stop treating the star as merely a lamp and start treating it as a fuel tank. At this level, the proposals involve directly ejecting the star's own material. You use magnetic fields to channel and expel plasma from the surface in one direction, or you use lasers to ablate material off one hemisphere, driving it away and pushing the star the other way. Or you engineer the star's own stellar wind, which every star has anyway, into an asymmetric flow. In every case, the star loses mass and gains velocity, which is exactly how a rocket works, just performed on an object 1,000,000 times the size of the Earth. The most extreme versions in the literature go further still. Stellar lifting combined with artificial fusion, where you extract hydrogen from the star, fuse it in engineered reactors far more efficient than the star's own core, and expel the products at enormous exhaust velocities. Or magnetic and plasma sails, structures that interact with the star's own outflowing wind and magnetic field to produce continuous acceleration without ever touching the surface. I want to state clearly that none of this violates any law of physics that we know. It requires engineering capabilities so far beyond ours that the comparison is not useful, but it does not require new physics. That is what makes it worth taking seriously as a category, rather than laughing at. It also has a serious problem, and honesty requires stating it alongside the appeal. The problem is time. Every one of these designs is slow. Class A in particular delivers an acceleration so small that reaching hundreds of kilometers per second takes an extremely long time, and reaching the higher rungs of our ladder takes longer still. Meanwhile, the stars in question are massive B-type stars, which we established earlier have lifetimes measured in a few 100 million years at most. So the timescale required by the technology and the timescale available from the star are in direct tension. You would need either a far more powerful design than Class A, meaning the higher classes with their vastly greater engineering demands, or you would need to accept that your engine outlives the star it is attached to, which rather defeats the purpose. That is not a rhetorical objection. It is a physical constraint, and it applies to the version of the idea that seems most naturally suited to these stars. But the real test of our hypothesis is never whether it sounds plausible. It is what it predicts, and whether the prediction survives contact with data. So let us go and look. Part 13. What an engine would look like. If somebody is pushing these stars, the pushing leaves marks. That is the useful thing about physical hypotheses, and it is what separates them from stories. There are 5 signatures we could look for, and we have looked for all of them. The first is the sharpest, and it is worth understanding properly because it does more work than the other 4 combined. A Hill's ejection is a single impulsive event. The binary comes apart, the surviving star departs with a fixed amount of energy, and from that instant onward nothing is pushing it. It coasts. Its path from that moment forward is determined entirely by gravity, which means it follows a trajectory that can be calculated exactly and rewound exactly. That is what ballistic means, and it is the same word we use for an artillery shell after it leaves the barrel. A stellar engine is the opposite. It thrusts continuously. The star does not coast. It accelerates, mildly and relentlessly, for as long as the engine runs. And a continuously accelerated path is not the same shape as a ballistic one. It curves in a way gravity alone cannot account for. Over hundreds of millions of years, that difference is not subtle. It is enormous. We can test that directly, because it is the exact same measurement we have been discussing all video. When you integrate these orbits backwards through the galaxy's gravitational field, do they converge cleanly on a launch point? Or do they fail to converge because something has been pushing them the whole way? They converge. Every measured hypervelocity star trajectory is consistent with ballistic motion following a single impulsive kick. That is precisely what the natural model predicts, and precisely what an engine would not produce. The second signature is waste heat. This one is unavoidable for any structure that intercepts starlight, and it comes straight out of thermodynamics. If you capture energy, you cannot capture all of it usefully. The remainder has to be radiated away, and for a structure surrounding a star, it gets radiated at infrared wavelengths. That is the classic techno-signature that people have been searching for around ordinary stars for decades. An object producing more infrared than its visible brightness can account for is the whole game. No hypervelocity star shows an unexplained infrared excess. The third signature is asymmetry. A mirror or a partial swarm covers one side of a star and not the other. That should produce a measurable difference in brightness or spectrum depending on which face is pointed at us, and since these stars rotate, that difference should vary in a detectable pattern. Nothing like that has been observed. The fourth signature is chemical. If something is processing a star's material, extracting hydrogen, running artificial fusion, or ablating one hemisphere, the composition of the atmosphere we can measure should drift away from what the star was born with, and here we have an actual high-quality measurement from the star we spent a whole part on. The abundances in HE 0437-5439 do not look processed or anomalous. They look like the Large Magellanic Cloud. They match a stellar population precisely, which is evidence about where the star was born and evidence against anything having tampered with it since. The fifth signature is statistical. Are there patterns in the population that natural models cannot reproduce? This is where the Leo clustering keeps coming up, because superficially it looks like exactly that. A non-random pattern, an organized distribution, something that looks like it has a direction, and therefore, to some eyes, an intention. Except a natural model predicted it, in print in 2016, before the data existed to check it. When your supposedly inexplicable pattern was written down in advance by the boring explanation, it has stopped being evidence for the exciting one. Now, there is a related claim that circulates alongside all of this, and it deserves proper treatment because the underlying observation is genuinely fascinating, and almost nobody has heard of it. There is starlight between the galaxies. That is not a metaphor. When you image a cluster of galaxies deeply enough, you find a faint diffuse glow filling the space between the individual galaxies, belonging to none of them. Astronomers call it intra-cluster light. It is the combined light of stars that have been torn loose from their home galaxies and now drift free in the shared gravity of the cluster. It is real, it has been measured, and in mature clusters it can account for a substantial fraction of all the starlight present. The claim goes like this: hypervelocity stars leave their galaxies permanently. Over billions of years, that should steadily add to the population of free-floating stars between galaxies. Older systems should therefore sit in visibly thicker envelopes of this diffuse light than younger ones. And when we look, we do not see that. Deep imaging finds intra-cluster light fractions of around 17% already present in clusters at high redshift, back when the universe was less than half its current age. The glow is there early, and it does not obviously build up the way a steady drizzle of escaping stars would predict. The claim then offers a solution. The stars are not accumulating in the void, because they are not being left in the void. They are being deliberately aimed at other galaxies, not ejected but delivered. The observation is correct. The inference does not work, and I want to explain exactly why, because the reasoning is instructive. Intracluster light is not produced by hypervelocity stars. It's produced overwhelmingly by tidal stripping. When galaxies pass close to each other, or fall into a cluster, or merge outright, the gravitational forces involved peel stars off their outer regions by the billion. Entire streams get pulled out at once. Simulations and observations both attribute the great majority of the diffuse light to that process, plus the general disruption of smaller galaxies falling into larger structures. Now compare the numbers. Tidal stripping liberates stars in their billions during a single galaxy interaction. Hypervelocity ejections, based on everything we have just spent an hour and a half establishing, occur at something like one detected event every few tens of millions of years per galaxy. The expected contribution of hypervelocity stars to intracluster light is therefore not small. It is negligible. It falls so far below any conceivable detection threshold that finding it would require an instrument nobody has proposed building. So failing to detect a contribution that nobody ever predicted would be detectable is not an anomaly. It is the expected result, arriving on schedule. And the early abundance of intracluster light is exactly what you would predict from processes that operate most violently during a cluster's chaotic assembly phase rather than gradually over its later life. The observation is real and genuinely interesting. The inference built on top of it is the error. There is one more correction I want to make, and it is the one I care about most, because it gets stated backwards constantly, and it matters for how people reason about everything else. The claim you will encounter is that the artificial explanation is actually simpler, that the natural model requires layers of special pleading, while the engineered explanation accounts for everything in one move, and therefore Occam's razor favours it. That is not how the razor works. Occam's razor is about the number of assumptions you are required to introduce, not about how tidy the story feels once you have introduced them. The natural explanation asks you to accept a quiescent black hole in a dusty dwarf galaxy. We know black holes exist. We know most of them are quiet. We know dwarf galaxies are dusty. We know our instruments struggle with faint objects at that distance. Every component is an object or a condition we already have independent evidence for. The alternative asks you to accept the existence of a civilization we have never detected, operating engineering projects we have never observed, on a scale we cannot imagine, leaving behind not one of the 5 signatures its own physics requires, in a galaxy where nothing else out of the ordinary has ever been found. That is not fewer assumptions. That is a great many more, and every one of them is unsupported. So here is my actual verdict, and I want to give it without contempt, because the people asking these questions are usually asking them in good faith. Stellar engines are physically permissible. The mathematics works. A sufficiently advanced civilization could, in principle, build one, and the design space is genuinely worth understanding, both as engineering and as a guide to what we should be watching for. If we ever do find a star whose trajectory requires continuous non-gravitational acceleration, this literature is where we will start. And there is currently zero observational evidence that any hypervelocity star is one. Not weak evidence. Not disputed evidence. None. The reason this idea has any oxygen at all is the same reason this video exists in the first place. There is a hole in the middle of the story, and the hole is that nobody has ever seen the black hole. Part 14. The wreckage is the evidence. Let me put the whole thing back together because you have earned the summary. Something in the Large Magellanic Cloud has been catching pairs of stars, tearing them apart and throwing one half of each pair out into intergalactic space at hundreds of kilometers per second. It has been doing this on and off for at least 400 million years. Roughly half of the fastest unbound stars in the Milky Way's entire outer halo point back to it. The physics that explains them requires an object of about 600,000 solar masses, and in the whole history of astronomy, nobody has ever recorded a photon we can attribute to it. Run the ladder one last time. 3i Atlas, the fastest interstellar object humanity has ever measured, cruising at 57 kilometers per second. The Magellanic population, 7 to 10 times that at ejection. HE 0437-5439 at 13 times. The galactic center ejections at 15. S5 HVS1 at 31. And J0927 at the top, 49 times faster than the object that made headlines around the world for an entire year. The fastest thing we have ever watched leave our solar system is the slowest rung on the ladder. But the number was never really the point, and I suspect you worked that out somewhere around the middle of this video. The point is what it took to find any of it. We are extraordinarily good at detecting the consequences of things. We are remarkably bad at detecting the things themselves. That is not a failing peculiar to this story. It is most of astronomy. Neptune was found because Uranus was not where the mathematics said it should be, and somebody worked out what mass, at what distance, would produce exactly that discrepancy, and then pointed a telescope at the calculated spot, and there it was. Dark matter was inferred because galaxies rotate faster at their edges than the visible material can explain, and nobody has ever detected a particle of it directly. Most of the planets we know about around other stars were found by watching a star dim very slightly on a schedule as something we cannot see passes in front of it. This black hole belongs to that tradition. We found it the way we find most of what we know, by noticing something moving strangely and asking what could possibly have moved it. Now widen the frame, because the timescales here deserve it. A star ejected from the Large Magellanic Cloud today will spend the next several 100 million years crossing the space between galaxies. It will not encounter anything, it will not be captured by anything, it will simply travel in a straight line under almost no external influence, for longer than our species has existed by a factor of thousands. And the ones ejected at the far end of the range we measured 400 million years ago left when this planet had only just begun growing forests. Every organism you have ever heard of, every event in the fossil record you learned in school, all of it happened while those stars were in flight. They are only now arriving in the outskirts of our galaxy. Consider where they end up. A star crossing intergalactic space is in a place with no meaningful gravity, no gas, and nothing to run into. It will burn through its fuel out there, entirely alone, in a region so empty that if it had planets, and if anything lived on them, that thing would look up at a night sky containing almost nothing. No band of the Milky Way, no neighbouring stars, just a scattering of distant faint smudges that are entire galaxies, so far away they would look like nothing much at all. Whatever civilization arose in a place like that would have to work extraordinarily hard to figure out that the universe was full of anything. These stars are not just leaving, they are being exiled into the emptiest environment that exists. Go wider still. The Milky Way and the Large Magellanic Cloud are gravitationally engaged, and one way or another, over billions of years, the smaller one is coming apart into the larger one. Whatever sits at the centre of that galaxy is eventually coming here. It will spiral inward, over an almost unimaginable span of time, and it will eventually meet Sagittarius A star. And when two supermassive black holes finally merge, they announce it in gravitational waves that will ripple out through the fabric of space itself. So the object we cannot see today will, in the extremely distant future, produce one of the loudest events in this corner of the universe. It just will not be quiet enough to hide by then. We have always assumed that the fastest things in our sky are the things passing through it. Visitors, objects from elsewhere, briefly crossing our view on their way somewhere else, and 3i Atlas was the finest example we ever got. But what if the fastest things in our sky are not visitors at all? What if they are refugees, thrown out of somewhere, by something, and still running? I want to end where the honesty requires me to end rather than where the drama would prefer. The conservative reading is almost certainly correct. There is a black hole of around 600,000 solar masses sitting in the Large Magellanic Cloud, doing exactly what the physics says such an object should do, and it is invisible because it has nothing to eat and because it sits behind dust at a distance where our instruments run out of sensitivity. The stellar engines are a fascinating detour with no supporting evidence. The intracluster light is explained. The clustering was predicted. The mechanism was demonstrated in our own galaxy years ago. That is the answer, and it is not a disappointing one. It is a very good piece of science, built carefully, stated honestly, with its assumptions on the surface where anyone can check them. And underneath all of it sits a fact that I cannot get past. The most powerful object in our galactic neighbourhood is known to us entirely through what it throws away. We have never weighed it directly. We have never watched a single star orbit it. We have never seen it. Every single thing we believe about it, including that it exists at all, we deduced from the wreckage. Which brings me to the one thing that could change all of this, and it is not a theory. It is a coordinate. The analysis has produced an address, roughly 1.5 degrees off the bright optical centre of the Large Magellanic Cloud, about 3 full moon widths away from where anybody would naturally look. There is a patch of sky where the backtracks converge. Sooner or later, somebody's going to point a very large telescope at that exact spot. If they find something there, then a black hole that is hidden from every instrument we have ever built finally has a face, and one of the most significant objects in the local universe stops being an inference. If they find nothing, then 21 stars are still leaving. They still have to have come from somewhere, and every explanation we currently have runs out at once. Nobody has reported the result of that search. As far as I can tell, nobody has publicly announced they are even conducting it. But the coordinate is published. It is sitting there in the literature waiting.